Hello, this time I'm going to go over the key to the calorimetry worksheets that I've handed out. So before I get started on that, I wanted to take a moment to say a couple things about calorimetry. So the first thing you have to understand is what it is. So the whole point of calorimetry is to measure the heat flow that occurs between two different substances. And so what we use is this device, which is called a calorimeter, which is displayed over here. Basically, the point of this device, you can see it has, in its most basic form, it has some styrofoam cups on the outside. Those are meant as insulators to make sure that no heat gets in or out. And then it has a lid to keep things in. And so what you'll do is you'll take a substance and you'll stick it inside of this calorimeter. And the whole point there is that, the heat that comes off of the object will go into whatever liquid you have in the calorimeter, and then hopefully you should know the specific heat of the liquid in the calorimeter, and then by measuring the temperature change of that liquid, you can figure out how much heat has left the substance that you put in, and if you know the mass of that substance, you can find its specific heat. And so if you look over here on the side, you can see that I have these equations here. Negative Q of substance equals Q of surroundings. What this is saying is whatever heat that you have that leaves the substance that you put in the calorimeter, it should go into the surrounding substance. Usually the surrounding substance is water, so that's nice and convenient. We know that it has a specific heat of 4.184. And so then basically what we get is this second equation here, negative MC delta T for the substance equals MC delta T for the surroundings. And I should say this all has to do with the law of conservation of energy. Because this is an insulated container, anything that leaves the substance that you put in has to go into the surrounding water because it can't leave the vessel. Because energy can't be created or destroyed, it can only go from one thing into the other. So that's where these equations come from. And so what we have essentially here is an equation with 6 different variables. And so you set it up, you write out the equation, and then you just kind of plug in the things that you know. So going here to the first problem, I'll go ahead and just let you read it here for a second. And if you need to pause the video, go ahead and do that. And try and figure out here what they're asking for. What piece of information are they asking for? Okay, if you've had a second to look at it, you should see that it says here at the bottom, use this information to calculate the specific heat of lead. Okay, it says then compare it to the value of the specific heat given on your specific heat tables. The other thing here is it said, for these problems, it's understood the specific heat of water is 4.184 joules per gram degree Celsius. So we'll be using that a lot, as I said. And the idea with a calorimeter is that you'd put some sort of liquid in there that you know the specific heat of. So that's why we use water most commonly, because it has a known specific heat, and it's a relatively high specific heat. So that means that it can tolerate, some pretty high temperature things being put inside of it. So setting up this equation, we get negative MC delta T for the metal equals MC delta T for the water. The thing that's unknown here is C for the metal. So that's that C there on the left-hand side of the equation. It's important to keep in mind that the left-hand side of this equation is talking about the metal, and the right-hand side is talking about water. So now we just need to plug in the 5 other things that we know. So really it's negative, and then the mass of the lead there you can see is 30.0. C is what we're looking for. Delta T, it goes from 200.0 degrees Celsius down to 27.8 degrees Celsius. Notice here it's out to the 10th place, and the temperature is going down, so that's negative 172.2. For the water here, it's going from 20 degrees Celsius up to 27.8. So we'll see here in a minute, its change in temperature actually results in something a little bit funny happening here, but I should say both of them end up at the same final temperature because what's happening here is you're putting two substances together and you're kind of waiting for them to reach the same temperature together. So going on here with the mass for the water, it says it's 25.00 grams. Then the specific heat of water is a known value. We said it's 4.184. And then the delta T, as I said, it's going from 20 degrees to 27.8. Sig fig rules for subtraction, this ends up giving you 7.8 degrees difference. Notice here that that has two sig figs with the way that it works with subtraction rules. So that actually ends up meaning that in the end, all that we have left here is a bunch of multiplication, sort of multiplication division problems. And so in the end, we're going to end up with two sig figs. So if you multiply that through, you get 5,166. C equals 815.88. Okay, notice I've kind of just not thought about the sig figs yet. I'm just going to go ahead and do that at the end. So here at our final answer, we divide both sides by 5,166, and I get C equals 0.16 joules per gram degree Celsius. Now, it says to compare this to the value for lead on your table of specific heats. You should see that the value for lead is 0.158 joules per gram degree Celsius. So this is pretty close. It looks like we've done a good job here. Problem number 2, this one here is also looking for C for the metal. So it's pretty much exactly the same process. We have negative MC delta T for the metal equals MC delta T for the water. In this case, our mass is 15 grams of the metal. C is unknown. Delta T for the metal, it goes from 481 down to 29.2. Because 481 is only given to the ones place, that's what the answer to this has to be in. So even though it's not what your calculator would spit out, 481 minus 29.2 gives you negative 452. And that equals 50 grams for the water, 50.0, times 4.184. So that's that known specific heat for water. And then change in temperature for the water is going from 25 to 29.2, so that's a difference of 4.2. All right, so looking at this one, notice we have two sig figs again, both because of the 15 on the left side of the equation and the 4.2 on the right side of the equation. We solve this, we get 6,780 C equals 878.64. Divide that out, we get C equals 0.13 joules per gram degree Celsius. And so if you inspect your table, you should see that this falls pretty close to gold. If you round there, because the sig figs on this are a little bit different than the sig figs on the table, you find out that this is probably gold. For problem number 3 here, this time, again, go ahead and look through it and try and figure out what it's asking in this problem. I'll give you a second, and if you want to pause the video, you might want to do that so you can think about it. Okay, what this says it's asking for says find what mass of aluminum was used. So we're looking for mass on the side of the metal. In this case, we have negative MC delta T for aluminum equals MC delta T. And it says this time the liquid inside of the calorimeter is chloroform, so on that side there, on the right-hand side, we're not going to be using 4.184. We'll be using the specific heat for chloroform. For both of these, we can look at our table of specific heats because it's instructed us to do so in this problem. And so it starts off this way. Negative M is the unknown. C for aluminum is 0.897. Delta T for the aluminum is negative 247 equals. The mass of chloroform used is 35.8 grams. C for chloroform is 0.960. And then its change in temperature is 31.2 degrees Celsius. And so looking at that, again, we're just going to try and see how many sig figs here. It looks like everything has 3, so our answer will have 3. Simplifying this side down, we get 221.559 M equals 1072.28. And then solving for M, we get that it's 4.84 grams of aluminum. Problem number 4 here. Looking at this one again. Try and figure out what it's looking for in this problem. All right. So it says, what was the initial temperature of the zinc? So I should point out that it's not asking for the change in temperature, it's asking for the initial temperature of zinc. So in order to solve this problem, we have to remember that delta T is defined as the final temperature minus the initial temperature. So what we're looking for in this case is Ti for the zinc metal. If I set this up, I get negative 2.50 grams for the zinc, 0.390 is the specific heat. It's given to us in the problem. And then we know the final temperature of both of these is 22.50. And then minus Ti. Because again, remember that delta T term is just TF minus Ti. So our final temperature is 22.50. Our initial temperature is Ti, and that's the unknown in this case. For the water, it starts out at 65.0 grams times 4.184 for its specific heat, times its change in temperature, which is 2.50 degrees. We can go ahead and solve that side. It's 680 point, and then on this side, we get it's negative 9.75 times 22.50 minus Ti. Distributing that negative 0.975, oops, I should fix this. It's 0.975. Distributing that through, we get negative 21.9 plus 0.975 Ti equals 680. All right, now we're going to do an addition problem. So it's 680 point plus 21.9. Our answer here needs to go out to the ones digit because that's what the 680 point goes out to. So this side ends up giving us 702. This side is 0.975 Ti. All right, dividing both sides by 0.975, we see that Ti equals 720 degrees Celsius. 3 sig figs there at the end. All right, working on the last problem here. This is certainly the most rigorous problem on the sheet. I would say in this process, don't worry too much about sig figs because, with the rigor of the problem, I think throwing sig figs into it just makes it a little bit too hard. So going through here, again, we're going to set it up exactly the same way, except right now what's not known is the final temperature, and that's the final temperature for both the metal and for the water. And so that variable shows up twice in this problem because, again, delta T equals TF minus Ti. And that final temperature is both the final temperature of the of the iron and the final temperature of the water. So we'll set it up -40 times C for iron is 0.444 from the table of specific heats times TF minus 135, because that's the initial temperature for iron, equals 100.0, the mass for water. C for water is 4.184. Delta T for the water is whatever that final temperature is, minus its initial temperature, which is 12. Okay, just doing a little simplification of what's on front of both of these sides here. This comes down to -17.76 TF minus 135 equals 418.4 TF minus 12. Okay, distributing that -17.76 through, we get -17.76 TF plus 2,397.6 equals 418.4 TF minus 5,020.8. So what we're going to do is we're going to bring the TFs to one side and bring the constant numbers to the other side. So we're going to go ahead and add 17.76 TF to both sides and add 5,020 to both sides. And then what we get here is 7,418.4 equals 436.16 TF. Divide both sides by 436.16, and we get 17.0 degrees Celsius equals TF. And that is the final answer there.